Welcome to Mathematical Finance. Today, we are going to explore one of the most fundamental concepts in the entire financial world, the zero rate. Imagine locking your money in a vault where it quietly grows untouched until the very end. Understanding this pure form of interest is the absolute first step to pricing almost every complex financial instrument. Let us dive in. Now that we know what we are looking at, let us define it clearly. Why does this concept matter? In the real world, most bonds pay you a little bit of interest every year, called a coupon. This makes the math messy because you have to reinvest those small payments. A zero rate strips all of that away. It applies to an investment that pays absolutely nothing until the final maturity date. Because there are no intermediate payments to worry about, it gives us a direct, unambiguous link between money today and money in the future. Before we move on to the math, let us see this visually. What you're looking at is a typical zero rate curve, often called a yield curve. The horizontal axis shows the time until maturity in years, and the vertical axis shows the corresponding zero rate as a percentage. Notice how the curve slopes upward? This visually represents a core financial principle. Locking your money away for a longer time generally earns a higher interest rate. Financial professionals monitor this exact curve constantly because it reflects the market's expectation of future economic health. With that visual in mind, let us think about how money actually grows over time. If a bank pays interest once a year, your money grows in discrete jumps. But in mathematical finance, we do not wait a whole year or even a month to add interest. We assume interest is calculated and added continuously, every single fraction of a second. This is called continuous compounding. It is a smoother, more natural way to model growth, and it makes the mathematics of pricing complex derivatives much cleaner and more consistent. This brings us to the fundamental equation for continuous compounding. Conceptually, this formula takes money today and pushes it forward in time. Let us look at the symbols. V0 is your present value, the money you invest today. Vt is the future value you will receive. R is the continuously compounded zero rate, and T is the time in years. The letter E is the mathematical constant for continuous growth. If you increase the time t or the rate r, the exponential term grows rapidly, meaning your future wealth increases significantly. Now that we know how to move money forward, what if we want to move it backward? This is called discounting. We simply rearrange our previous formula by dividing both sides by the exponential term, which gives it a negative exponent. The negative sign is crucial. It means we are pulling a future amount, Vt, backward in time to see what it is worth today, V0. Notice that as the zero rate R increases, the present value decreases. A higher interest rate means you need to invest less money today to reach the same future target. Before we move on, let us see this with a concrete example. Suppose the 5-year zero rate is 5% per annum, and you invest $1,000 today. How much will you have in exactly 5 years? We are given the present value, the time, and the rate. First, we must always convert the percentage rate into a decimal. So 5% becomes 0.05. Then, we substitute these known values into our future value formula. The initial 1000 sits in front and the exponent becomes 0.05 multiplied by 5. Continuing with our calculation, we multiply the rate and time to get a total exponent of 0.25. This multiplication represents the total accumulated rate over the entire period. Next, we evaluate e raised to the power of 0.25 using a calculator, which gives us a growth factor of approximately 1.2840. Finally, we multiply this factor by our initial $1,000. The final answer is $1,284. This means your money earned $284 in pure interest over the 5 years. Now let us look at the exact opposite scenario. Suppose you are promised exactly $1,000 in 5 years and you want to know how much that promise is worth today. We are given the future value, the rate, and the time. Because we are pulling money backward in time, we use the present value formula with the negative exponent. We substitute 1000 for VT, 0.05 for the rate, and 5 for the time. The negative sign ensures we are shrinking the future value down to today's terms. Let us finish this discounting calculation. The exponent simplifies to negative 0.25. When we evaluate this negative exponential, we get a decimal less than 1, approximately 0.7788. This is our discount factor. It tells us that a dollar in 5 years is only worth about 78 cents today. Multiplying this by 1000 gives a final present value of $778.80. Receiving $1,000 in 5 years is mathematically identical to having $778.80 in your pocket right now. Let us try a slightly more complex problem. You are offered a zero-coupon bond that costs $800 today and promises to pay exactly $1,000 in 3 years. What is the continuously compounded zero rate for this investment? Here, we know the present value, the future value, and the time, but the rate R is unknown. We start by plugging our known values into the future value relationship. The initial investment of $800 goes in the present value spot, and the final payout of $1,000 goes in the future value spot. Continuing with our algebra, we need to isolate the exponential term. We divide both sides of the equation by 800. This creates a simple ratio of the future value to the present value, which simplifies to 1.25. This means your money grows by 25% over the total 3-year period. But we need the annualized rate. To bring the unknown rate R down from the exponent, we take the natural logarithm of both sides. The natural logarithm is the exact mathematical opposite of the exponential function, allowing us to unlock the exponent safely. Let us find the final rate. The natural logarithm of 1.25 is approximately 0.2231. On the right side, the natural logarithm completely cancels out the exponential e, leaving just the exponent, 3r, standing alone. We divide both sides by 3, which represents the number of years. Dividing the total logarithmic growth by the time gives us the annual continuous rate. The final mathematical result is 0.0743 or 7.43% per year. This is the true return on your bond. Now that we have used this formula extensively, let us understand where it comes from. This chunk of the derivation establishes the mathematical bridge between standard banking and mathematical finance. We start with the standard discrete compounding formula, where the variable m represents the number of times interest is paid per year. To model continuous compounding, we imagine slicing the year into infinitely many tiny moments. Mathematically, we do this by taking the limit as m approaches infinity. This setup perfectly captures the physical idea of interest being calculated and added every single fraction of a second without ever stopping. Let us conclude this derivation and see the final result. As the number of compounding periods m approaches infinity, the complex expression inside the limit resolves to a very famous mathematical constant. The limit of 1 plus r over m, all raised to the power of m, is the exact mathematical definition of Euler's number, e, raised to the power of r. By applying this standard limit, the messy fraction completely disappears. This gives us a final elegant result. Vt equals V0 times e to the power of RT. This constant E is the absolute foundation of continuous growth in nature and finance. So we have proven where the formula comes from and how to use it. This brings us to a crucial question. Why do we care so much about zero rates in the real world? If you try to compare two different bonds with different coupon sizes, it is like comparing apples to oranges. Zero rates solve this problem by breaking every financial instrument down into its atomic parts. A complex coupon paying bond is simply viewed as a collection of individual zero coupon bonds, one for each cash flow. Without zero rates, the entire modern financial system would lack a consistent way to value money. We have covered a lot of ground today, so let us summarize the most important ideas. First, a zero rate is the purest measure of interest, representing the growth of money when there are no intermediate payments. Second, by using continuous compounding and the exponential function, we can easily translate future cash flows into their present values, and vice versa. Moving money forward is compounding, and moving it backward is discounting. Mastering these zero rates is your absolute first step to pricing any complex derivative. You now understand the core engine of financial valuation.